Okay guys, in this video we're going to discuss the next topic of Focus 2. This will cover enthalpy. The way I like to think about enthalpy is that it's a convenient way of representing energy when you're considering processes at constant pressure. So enthalpy is an energy. It has the symbol H and it's measured in units of joules or kilojoules. Like the internal energy, it is an extensive state function, and here is listed its formal thermodynamic definition. So the enthalpy is the internal energy of your system plus another energy term given by the product of pressure times its volume, the volume of the system. So it is an energy, but it's not a fundamental energy like internal energy, right? Internal energy was the average of all of the kinetic and potential energies of all of the particles within your system. Enthalpy is that plus this extra term. We are going to be looking at both infinitesimal and finite formulas involving enthalpy. And so what I've presented here, this is how you would take the differential of enthalpy. So taking the formal definition and then applying the d to the enthalpy, you would get du plus d acting on PV. And to calculate this term, or to expand this term, you would use the product rule from calculus. See here how I have pressure times dV plus volume times dP. I've deployed the product rule. If you're looking at finite changes in enthalpy, you can consider the finite change in each term separately. However, when you're working with the delta, you may not apply the product rule. So you can't apply the product rule to this term. That's what I wanted to point out here, and how to calculate a difference between the infinitesimal change and the finite change. Well, on the next slide here, I've taken a figure from the textbook, which is used to explain the difference between internal energy and enthalpy. So suppose that you have a system that has a constant volume, so a rigid container, and you transfer some energy to that system. What will happen is that the energy that's transferred in, say as heat, will go directly into changing the temperature of the system and the internal energy. And so you'll heat up the system, of course. Now, when the system has the ability to change its volume, okay, so when volume is not constant, but rather when pressure is constant, energy that's transferred into the system as heat gets split into two parts, essentially. One part goes into changing the internal energy of the system and increasing the temperature. However, another part of the energy goes into expanding the system, right? Now that you have a constant pressure process, the volume of the system will typically get larger if you transfer in some heat. And so that will be energy lost as work. So when you have an isobaric system and you heat it up, some of the energy goes into increasing the temperature of the system, but then another portion of that energy goes into expanding the volume. That is, you lose some of that energy as work. Here we're looking at that finite enthalpy change in a little bit more detail. I've rearranged it a little bit, and we're considering two cases. In the case of the condensed phases, we're looking at the difference between delta H and delta U, so this delta PV term. And here I've expanded it as pressure final, volume final minus pressure initial, volume initial. For solids and liquids, volume does not change very much with pressure, and so this term is effectively zero for most condensed phase systems at ordinary pressures. Right? You'd have to go to really high pressures in order to change the volume of a solid or of a liquid. So for ordinary pressures, this difference is negligible, and delta H and delta U are practically the same. For gaseous reactions, however, or any processes involving gases where the gas is a compressible fluid, here the delta PV term is usually very significant. And if you've got an ideal gas under isothermal conditions, for example, if you're talking about a gaseous reaction, you can write this delta PV term as the change in the number of moles of gas times R times T. And so just depending on the chemical reaction, this may be, a number like 2 or 3, something like that. And so that term is often significant. Okay, so there's a big difference between delta H and delta U for gaseous problems, but a small difference typically for condensed phase problems. And so here, this problem is essentially illustrating that fact. Okay, so we're looking at a condensed phase problem. We're talking about calcium carbonate in the form of calcite that's being converted to a different solid, argonite. Okay, and we're told that the change in the molar internal energy is 0.21 kilojoules per mole. We're being asked to calculate the difference between the molar enthalpy and internal energy changes when the pressure is 1 bar, and then we're given some information about the mass densities. So here we would be calculating this difference. This is what they want us to calculate. Okay? And this is going to be equal to that delta PV term here. In this case, pressure is constant, 1 bar. So the pressure can come out of the delta. And so it's going to be pressure times delta V. This pressure is 1 bar. So, and I should make these molar volumes since I'm looking at the molar difference here. So we want to calculate the change in the molar volume for calcium carbonate when it undergoes this reaction. So we can write the change in the molar volume. We can write it as the mass. Let's see, we'll take the mass of the calcium carbonate, and we want to take that times 1 over the density, and we'll make that the argonite. I'll just call it A, minus 1 over the density of the calcite, call that C. So this is going to be mass, and then we have mass over volume, and so we want to divide that by the molar mass. Right. Let me just check out the units real quick. We're going to have grams divided by grams per mole, and this will be volume per mass in grams. And so it looks like I don't need that. What I needed to do was just multiply by the molar mass. So that's going to have the right units. So we've got grams per mole. Then we're going to have whatever volume unit we use divided by grams. So that's going to work out. So that's going to be our volume per mole which is what we want here, molar volume. So pressure is, I'm going to do the calculation over here. I need a little bit more room for some of the unit conversions. We're going to have 1 bar, and then the molar mass, 100.1 grams per mole. And then for the densities, it's going to be, we want argonite, so 1 over 2.93 grams, and that's in cubic centimeters, minus cubic centimeters. For the calcite, 2.71 grams. And what I'd like to do is express the cubic centimeters in units of liters. And so I'm going to take 10 to the minus 2 meters per centimeter and cube that, and then 10 decimeters per meter, and we need to cube that. Okay, so this is going to give us units of bars times cubic decimeters, which is bar liters, and then we'll convert that to joules. So just do the calculations here. So I'm getting minus 2.77 times 10 to the minus 3, that's units of bar liters. And then to convert that to joules, we would multiply by 100 joules per bar liter. And so we get minus 2.77 times 10 to the minus 1. And so we'll just write that as minus 0.277 joules, which is a very small energy difference. Okay, so the difference between delta H and delta U per mole is quite small. In fact, that would be units of joules per mole. In fact, I left out that 1 over mole in the units. Okay, so the difference between delta U and delta H for the condensed phase is very small. In this follow-up problem, we're doing the same thing, but for a gaseous reaction. And here we're going to find that there's a big difference between delta U and delta H. So in this case, delta H minus delta U equals delta PV. In this case, we're dealing with a gaseous system, and so we wind up with so for isothermal conditions, we get this equation. In this case, there's the delta N. There's 0 moles of gas in the products and 3 moles of gas in the reactants, so delta N is minus 3, and then we've got 8.314 joules per mole Kelvin, and the temperature is 298 Kelvin. So we'll do this calculation. And you get minus 7,432. That would be 0.7 joules. Okay, so you can see that that's a lot larger, and that would be per mole of reaction. That is a much larger number for this reaction than it is for the condensed phase reaction that we looked at. So for gaseous reactions, there's a big difference between delta H and delta U. we'll turn to the next topic here. So we'll talk about isobaric heating. Recall in the last video we did isochoric heating, and one of the main results that we found for isochoric heating was that when you have constant volume, delta U equals the heat, right? So the change in the internal energy equals the isochoric heat. What we're going to find in the case of isobaric heating is that the enthalpy change for the process equals the isobaric heat. So the change in enthalpy is equal to isobaric heat when no non-PV work is possible. The external pressure is constant. In this case, we can write it infinitesimally or we can write it as a finite change, it doesn't matter. We have this result. The enthalpy, H, increases with temperature under constant pressure by an amount determined what's called the isobaric heat capacity. Previously, we looked at how the internal energy changes with temperature under constant volume conditions. Now we're looking at how the enthalpy changes with temperature under constant pressure conditions. So here's the infinitesimal relationship between the change in enthalpy and the change in temperature. In general, that heat capacity at constant pressure is a temperature-dependent function, and so you have to do, in the general case, you have to do an integral like this. And this is very similar in structure to what we looked at before for isochoric heating. Here we're being asked to do a little derivation. They want us to show that delta H equals Q for an isobaric process. So I'm going to just, let's start with just the definition of enthalpy. So here's the definition of enthalpy. And what I'll do is I'll take the differential. So we'll get dH equals du plus dPV. And I can use the product rule to expand this. So I'll do that. And now we'll use the first law to expand du. For infinitesimal changes, when there's no non-PV work present, this is going to be equal to minus PdV. This is the work. And what you see is that this term cancels out that term. For the case of isobaric conditions, that term is also equal to 0. And so you're left with dH equals dQ, and the finite version of this would be delta H equals Q. Okay, and that's what we were asked to show. So for isobaric conditions, where there's no non-PV work, the change in enthalpy is equal to the isobaric heat. Oops. This figure illustrates that enthalpy is a temperature-dependent function, and this slope of the enthalpy with respect to temperature is equal to the isobaric heat capacity. And that is also a temperature-dependent function in general. So here we have the enthalpy at two different points. The slope that's tangent to the curve, this is the definition of the heat capacity, is different at these different points. Comparing this to the same result, the same curve for the internal energy, we also see that the enthalpy is larger, and also in this case, and the slope of the slope of the lines, the slope to the curve is also larger. So the heat capacity at constant pressure is also larger than the heat capacity at constant volume. Here we're being asked to do a quick little calculation involving isobaric heating. Calculate the enthalpy change when 0.798 grams of boiling water is vaporized at 1 atm using an electric current of 0.5 amps from a 12-volt supply for 300 seconds. Really, this is just a test of your ability to work with these electrical units. So here we've got heat. It's going to be equal to the current, which is coulombs per second, times the number of seconds that it's being operated, 300, that would be seconds, and then the voltage, 12 joules per coulomb. That's what a volt is. And so this is going to give us the joules. So I'm getting 1800 joules out of that calculation. So that's how much heat was required to vaporize the water. Now they want us to calculate the enthalpy of vaporization per mole. So this, in fact, is equal to the enthalpy change for the process, because it's constant pressure. To do it per mole, we need to divide by the number of moles. So the enthalpy of vaporization is going to be this 1800 joules we want to divide by the number of moles, which is going to be the mass, 0.798 grams, and that's going to be divided, let's see, that's going to be multiplied by 1 over the molar mass for water, 18.02. And if I convert that to kilojoules, you get 40.6 kilojoules per mole from this calculation. A little bit more depth on the isobaric heat capacity. So here we've got, the isobaric heat capacity is an extensive state function, and it's formally defined as the partial derivative of the enthalpy with respect to temperature while retaining pressure constant. Here we have, so this is an extensive function, so the value of the heat capacity depends upon the size of the system. The intensive version of heat capacity, which is the molar isobaric heat capacity, has units of joules per Kelvin per mole, or you could also write that as a specific heat capacity, joules per Kelvin per gram, by dividing the heat capacity by the mass of the sample. Just like the isochoric heat capacity has a particular value for different substances, so does the isobaric heat capacity. Here is a common polynomial form for expressing the heat capacity's dependence upon temperature, A plus B times T plus C divided by T squared. And here are the parameters A, B, and C for different substances. And we're being asked to work with this formula in this problem. What is the change in the molar enthalpy of N2 when it is heated from 25 degrees Celsius to 100 degrees Celsius. What I'm going to do, I'm going to complete part of the problem, but I'll leave the rest, the numerical details, as an exercise for you. What I will show you is that here's how you calculate an infinitesimal change in the enthalpy for constant pressure processes. Okay. And then to get the finite change, you would integrate both sides. That gives you delta H here. And then what you would need to do, you can pull the n out, and then we'll substitute in that polynomial form. A plus b times t plus c over t squared dt. And now you want to integrate this guy. And so the first term is going to give you a times tf minus ti. The second term is going to give you b over 2 times tf squared minus ti squared. And then the third term, negative c 1 over t f minus 1 over ti. Okay, so that's the integrated expression. And then in order to solve the problem explicitly, to get the digits, you would plug in, using units of Kelvin, Ti is the 25 degrees Celsius and Tf is the 100 degrees Celsius. And then you would need to substitute in the values of A, B, and C for nitrogen into that formula. So I'm going to leave those details for you to try out on your own, but that's how you would solve the problem the rest of the way. In this next example, we're being asked to derive expressions for the enthalpy for and the isobaric heat capacity for a perfect gas. So I'm going to go back to that formal definition of enthalpy, and then we'll consider the case for an ideal gas. Previously, we have shown that the internal energy for an ideal gas is given by the number of kinetic degrees of freedom divided by 2 times nRT, so that's U. And then for an ideal gas, pressure times volume is nRT. So we have d plus 2 plus 1 times nRT, and we can rearrange that. We can write it as d plus 2 over 2 times nRT. So here's the formula for calculating the enthalpy of an ideal gas, where d is the number of kinetic degrees of freedom. So for a monatomic gas, d is 3. For a diatom, d would be 5. For a polyatom, d would be 6. To calculate the isobaric heat capacity, what we would do would be to take the enthalpy and then divide it by, or not divide it by, take the derivative of the enthalpy with respect to temperature at constant pressure. This expression doesn't depend upon pressure, it only depends on temperature, and so we get d plus 2 over 2 times nR. So for the ideal gas, we see that the heat capacity is a constant. It doesn't depend upon temperature. Here's some additional relationships involving heat capacity that are useful to keep in mind. For perfect gases, you can show that the isobaric heat capacity is the isochoric heat capacity plus the gas constant. So this is one relationship that we're going to use often. And then another important thing to realize is that for solids and liquids, under ordinary pressures, the difference between the isobaric and isochoric heat capacity is essentially nothing. Okay, so they're basically the same for solids and liquids. when the pressures are low. If you go to very high pressures, of course, then there will be differences between them. Okay, so keep that in mind. The next set of slides correspond to gas expansion problems where we're going to be calculating heat, work, delta U, and delta H. These are very important problems, so I'm going to save them for the next video. So I'm going to stop this one right here, and then we'll go over these problems in a future video.